Hello, I'm going to present you with our group design assignment for Mechanical Engineering 1000. I'm your presenter for this presentation, Joel Berg. Introduction. Our goal was to create a small robot vehicle that would traverse a course that is 8 foot by 8 foot. This vehicle would have the ability to avoid obstacles, make a decision on which direction to turn by comparing left and right distance, and stop on a 4-inch by 4-inch black square. We tested this vehicle on November 30th, 2021. Through many trials and fixes, we were able to get the Arduino-controlled car to stop on the black square, although many adjustments were made to the original design. This included changes to the location of the infrared mount, calibration, battery configuration, and discarding a couple of other mounts that didn't quite fit together after printing. A few pieces of code needed to be changed as well. Previous designs. These designs were made by Lawrence and illustrated by some of the visions our group had discussed in the beginning. One of the main questions we had was how many wheels would be enough. Not just how many wheels, but how many motors to drive them. For some reason, we decided on having 4 motors moving 4 wheels independently. Our thinking was that 4 wheels would be better for moving the vehicle over the ramps. The design was pretty much the same as our final, in that it involved a lower and upper chassis with the electronics mounted on top. Later, a bumper pressure switch was added because through testing, the ultrasonic sensor seemed to not have a good field of distance to measure. So here are some designs. This one has 2 wheels driving in the back and then a swivel wheel in the front. This one has 4 wheels. This one has 4 wheels, but only 2 are driven by the motor. And then this was more of our final design and what we chose to do, which is 4 wheels driven by 4 motors. Manufacturing plan. Our manufacturing was mostly done via 3D printing. We also used a lot of M3 screws, nuts, hot glue, jumper wires, a LiPo 8.7 volt battery pack, a 5 volt portable cell phone charger, a driver shield, a servo motor, an ultrasonic sensor, 4 DC motors, 4 wheels, a pressure switch, and of course the Arduino board. SolidWorks renderings. In the beginning of the design process for the actual vehicle, the bottom chassis was made first. This would mount the wheels and the IR sensor would go in the front hole. Although later during testing we discovered that our IR sensor needed to be placed in the very front of the vehicle, probably due to the fact that there was so little light that it couldn't detect the black square or detect when it wasn't on the black square. Some components like the DC motors and the pressure sensor were quickly built in SolidWorks to help with the scaling of the model. Later, the pressure sensor switch was engineered, printed, and mounted. The final step was to make the upper chassis and add component mounts. The servo motor fits snugly in the tan-colored mount on top of the chassis. Here's another rendering of the pressure switch mount. Methods and design process. Here's a picture of the printed out pressure switch mount. It is a simple design which utilizes brass hexagon spaces threaded at 3 mm on each end. Those are attached to the front bumper, then screwed into a back plate. This backplate is attached to an adjustable screw, just in case more room was needed between the front bumper and the pressure switch. The goal was to create a bumper that would push the switch at any time when running into any sized object at any angle. The prototype of the prototype phase had everything complete except for the top chassis. This helped with the wiring and also helped us discover the battery issues. We will cover these in a later slide. For the top, we used balsa wood as a temporary top chassis and mounting bracket for the for the servo and the ultrasonic sensor. To code the robot, each individual component was programmed separately. This allowed an understanding of how each program would work together with one another. The first component to be programmed was the DC motors. An individual program was written to make the motors move forward for a set time. Then we made a program to move backwards, move left, move right, and stop completely. Next, the ultrasonic sensors and servo motors were programmed together. The serial monitor was utilized a lot for this. The rest of the components were later programmed, such as the pressure sensor and the IR sensor. Again, serial monitor was very helpful for this. As stated before, there were many issues with the batteries. First, our driver shield seemed to be drawing a lot of current. When the Arduino board was plugged into the computer and the 8.7 volt battery plugged into the shield, the program ran perfectly and did exactly what was expected. When the Arduino board was unplugged from power, nothing happened. This led us to believe the Arduino board needed an extra power supply in order to work. Several battery chargers were tried until this red one in the picture was successful. During the final tests, we found that the battery lost power and the ultrasonic sensor also seemed delayed and did not function very well. Luckily, the pressure sensor switch made up for this lack of obstacle avoidance the ultrasonic sensor failed to detect. And for those of you who don't know, a driver shield is essentially a circuit board with several transistors on it that can help move the wheels independently forward and backward, supplying power to them based off of signals from the Arduino board. And it plugs in just right on top of the Arduino board through the pins. Here is the code diagram. This flowchart explains the code in action. After the setup phase, the loop instructed the car to scan for a black square using the IR sensor. This was first. If the black square was not detected, then the car moves forward. If the distance read by the ultrasonic sensor is less than 20 centimeters, or the pressure switch is pressed, the car is instructed to back up for 1 second, look left, get a left distance, look right, get a right distance. Then another statement says if the left distance is greater than the right distance, turn left and go back to the move forward mode. If this is false, or the else statement, then the car turns right and moves back to the forward phase. Outside of the loop, I just described the car would scan for the black square. This turned out to be a problem because if the car passed the black square when it was in any other mode except for forward, the car would not stop. More research is needed to learn to solve this problem. Here is a photo of our final design. You can see on the back we have the cell phone battery, then the LiPo hobby battery, then the driver shield, and under the Arduino board. The ultrasonic sensor attached to the servo in front, and the pressure sensor bumper. Analysis. Here's a video of our vehicle running through the obstacle course. This was after a lot of testing, so the ultrasonic sensor didn't scan all the time, it seemed, and we had to rely on the pressure sensor switch to be pushed. And sometimes it wouldn't even push it all the way. However, it did seem to do a good job in doing the left and right distance comparison and then choosing which direction to move into. It seemed to go over ramps pretty well. You can also see the green light. That green light is the IR sensor. As we discussed, it had to be attached to the front of the bumper because it just didn't work underneath the vehicle. Here's a video of the vehicle finally hitting a black square after several tests. It was getting pretty late into the night, so we were really hoping for it to eventually hit. Lastly, here is the vehicle running a pre-programmed track. And I'll just describe to you what the program was written to do. So after we press start, the vehicle runs for 3 seconds, turns right, runs for 3 seconds, turns right, runs for 2 seconds, turns right, runs for 1 second, turns left, and then it hits the black square. It did as it was intended. What could be done differently? Next time, I think using 2 motors and 2 wheels would be better. Or sorry, using 2 motors and 4 wheels, or maybe 2 wheels and just 1 wheel on a swivel. Using 2 motors would draw less current from the system and give more to the other components. From some online research, it turns out that the driver shield we were using is apparently very inefficient, and the transistors suck up a lot of energy and lose it to heat. A better driver or transistor system might be better. It would be awesome if there was a design that would only run on 1 power source, seeing as that using 2 batteries was very heavy and also quite annoying. As stated before, the ultrasonic sensor didn't seem to run well. You could tell in the video that the pressure sensor was mostly utilized and not the ultrasonic sensor for obstacle avoidance. Lastly, more research is needed to be done to code for scanning the black square when inside the if statements and modes other than move forward. Conclusion. We made a vehicle that mostly avoided obstacles and eventually found the black square. The many components were drawing so much power that the ultrasonic sensor was lacking. It was a very good thing that we had a pressure sensor bumper. Otherwise, our experiments might have failed completely. Power consumption seems to cause a lot of issues, so more research and development is needed for later projects. Thank you.